Okay, let's unpack this. Have you ever stopped to think about how factories, manage to produce so many things day in, day out, so efficiently? How do they make sure every single step happens just right without wasting time? Well, today we're doing a deep dive into something absolutely key to that, assembly line balancing. It's a really foundational production strategy.
Yeah, it really is. And what's fascinating about assembly line balancing is its core idea. You set a target production rate first, and then you meticulously design the whole line you're distributing tasks, right? Among workers, machines, workstations, all geared towards meeting that specific time frame. The main goal, really, is to cut down on idle time, or ideally, just get rid of it altogether.
Exactly. And that's our mission for this deep dive. We're going to get into the source material you've shared, which does a great job explaining what assembly line balancing actually is. It highlights the crucial benefits, the why, and then walks us through this fantastic real-world example. It shows how a strategic tweak or rearrangement can lead to some really significant improvements. Think of this as your shortcut, your guide to understanding a core concept in manufacturing efficiency. So fundamentally, the whole point of line balancing is assigning the workload, right? So each workstation, each step, has roughly the same amount of work to do. It's all about creating this smooth, even flow. No bottlenecks, ideally, but okay, why bother? Why go through all this effort? What are the actual tangible benefits for a company?
Well, the source material is pretty clear on this. When you get assembly line balancing right, you see improved process efficiency overall. You get a higher production rate naturally. The total time it takes to make something goes down. And crucially, you're aiming for minimal or even zero idle time. That directly links to potentially boosting profits and cutting costs. If you look at the bigger picture, yeah, it's really about optimizing how you use your resources, your people, your machines, and that hits the bottom line directly.
Okay, this is where it gets really interesting for me. The source gives us this very concrete example, and it just brings the whole idea to life. So imagine a factory. They assemble a product on an assembly line, and they realize they need to rejig things. They need a better balance to cut down that workstation cycle time. The current setup involves 13 distinct activities, okay? 13 steps to make the product. And there are 5 workers or workstations handling these tasks. And one important rule, no backtracking. The product only moves forward.
Right, that's a common constraint. So first things first, you need to know the total actual work involved. You add up the time for all 13 activities. The source calls this total processing time, or TP, and it comes out to 350 seconds for this product.
Okay, 350 seconds total work. Now, the source then gives us the times for each of the 5 workstations in the existing setup. So workstation 1 takes 80 seconds. Workstation 2 is quicker, 60 seconds. And then workstations 3, 4, and 5 each take 70 seconds.
And this is key. The cycle time for the entire line, let's call it CL, isn't the average. It's set by the slowest workstation.
Yeah.
So in this existing setup, the maximum time is at 80 seconds at workstation 1. That 80 seconds is the drumbeat for the whole line.
Right, the bottleneck. And this leads to another really useful metric they mentioned, balance delay, which sounds a bit technical, but it's basically measuring the wasted time,
Right.
the unproductive slack in the system.
Exactly. It shows how much potential capacity is being lost because the work isn't perfectly even. And there's a formula for it, which the source provides. You look at the total time available across all stations versus the actual work time. For this existing line, using that formula, number of workstation cycle time, total processing time divided by number of workstation cycle time, times 100. It comes out to 12.5%. That's the balance delay. 12.5% of the time is essentially non-productive.
Okay, 12.5% idle time. So what does that actually mean for how many products they can make? What's the output look like?
Good question. So the source assumes they run 247, basically 3 8-hour shifts. The production rate, PL, is calculated as the total available time in seconds. So 24 times 60 times 60 divided by that line cycle time, the CL. So for the existing line, it's 24 by 60 by 60, 80 seconds. That gives you 1,080 units per day.
1,080 units. And you've got that 12.5% idle time hanging there. That might not sound huge to some, but in a factory setting.
Oh, absolutely. 12.5% inefficiency on a line running constantly. That's significant. It means time, money, and potential output are just evaporating.
So a manager sees this. They see workstation 1 is the holdup. They see the 12.5%. What's the immediate thought process?
The immediate thought is, how can we smooth this out? Can tasks from workstation 1 be shifted? Can we break down that 80-second job, maybe move a small part of it to workstation 2, which only takes 60 seconds? Or maybe even look at workstations 3, 4, 5. They all have 10 seconds of slack compared to the bottleneck. It's about redistribution.
Right. And this is exactly where the source goes next. It doesn't just diagnose the problem. It shows the solution, the balancing act. And the impact is, well, it's pretty dramatic.
It really is. So remember, we have 5 workstations and 350 seconds of total work. If you divide that total work, 350 seconds, by the number of stations, 5, the ideal average time per station is 70 seconds. So the goal of the rearrangement was to get every single workstation as close to that 70-second mark as possible.
And they managed it. The source shows that after reallocating the tasks, presumably breaking some down, shifting them around carefully, the new cycle time for the entire assembly line, the CL, is now 70 seconds.
Exactly. They hit the theoretical minimum cycle time based on the number of workstations. And the really amazing part, calculate the balance delay now. With every station at 70 seconds and a line cycle time of 70 seconds, the balance delay, DL, becomes 0%. Zero.
Wow. Okay, from 12.5% idle time down to 0, just by shuffling the tasks around intelligently. That's impressive.
It's the power of balancing. You're eliminating that slack entirely. Every workstation is now pulling its weight equally, you could say.
So let's connect that back to production. What does this new, perfectly balanced 70-second cycle time do for the daily output?
Okay, same calculation as before, but with the new cycle time. Available time is still 24 by 60 by 60 seconds. Divide that by the new CL of 70 seconds. The production rate jumps to 1,234 units per day.
1,234 units. Compared to the old 1,080, that's, let me see, an extra 154 units every single day.
Correct. An increase of 154 units.
Which, percentage-wise, is about a 14% increase in production.
Yeah.
Just from balancing the line. No new machines, no extra workers mentioned, just reorganizing the work.
Precisely. And that's the core takeaway from this example in the source material. It shows very clearly how smart arrangement and allocation of tasks, how it can seriously boost production, cut down the overall processing time per unit, and really push you towards an optimal level of output. It's all about getting more from what you already have. It's pure efficiency gain.
So, thinking about this, what does it all mean for you listening in? We've taken this deep dive into assembly line balancing, and we've seen through this really clear example just how powerful optimizing these processes can be. Simply rearranging tasks can lead to pretty substantial gains in efficiency and output.
Yeah, and the source really emphasizes this point. In manufacturing, it's not really a set it and forget it kind of thing. It suggests you should always be looking, always reevaluating. Are the tasks still balanced? Can we tweak things further? It's about continuous improvement to keep that effort balanced and production optimal.
It definitely makes you think. Next time you pick up, well, almost anything that's been manufactured, consider that invisible dance of efficiency happening behind the scenes, that assembly line balancing act that brought it to you. And it raises a bigger question, doesn't it? How many other hidden efficiencies like this are out there in all sorts of industries, just waiting to be found and optimized? What else could be running smoother, faster, better?